Hey everyone, welcome to my talk. Today I'm going to be talking to you about digital forensics applied to K8. Again, this is a part three of Enhancing Intruder Dilemma series I've been doing on containerization technologies. Just to expand here a little bit on what K8s is. So K8s does stand for Kubernetes. And the reason why we see the number 8 between the K and the S, that's because that's how many letters are in between those two letters. Little bit of a disclaimer. Again, anything you see here, this is really just my private research, and information that's just publicly available. None of this is a reflection, really on my employer or what it is that's going on there. Um, and again, just really enjoy the show. And who am I? So look, bottom line here is that I've been a big advocate, of sharing any of the kind of private research and learning I do, with my community, and you kind of see some of the stuff I've spoken on there on the slide. And then just kind of on a professional level, I've always tried balancing out, kind of both the academic side by, pursuing, collegiate, higher learning, and also, on the professional side, getting, different, certifications that have been relevant to work that I've done in my, my time working. Just kind of an overview. Just going to touch on, the differences again between, what is a container versus, what is a virtual machine. Also, want to give a little bit of an overview on what the Kubernetes environment looks like, and then address, why is it we would use a technology like Kubernetes, right? And we call this, container orchestration, and what does that really look like? And then finally, what are some of the deployment options when we start thinking about, how is it we might use a technology like Kubernetes? And then also, get in a little bit into the security considerations on how it is you might protect, your particular use of Kubernetes. And then really the kind of the sweet spot here for this presentation, which is what are some of the new layers of analysis that are really presented to us if there is potentially a compromised environment that's using Kubernetes, and then also from an incident response standpoint, right? Depending on where the compromise is at, what actions might we take? All right. So look, lots of great stuff here on the screen. Definitely addressed this in my talk on container forensics. So let me just kind of sum it up. Look, with virtualization, we're really dedicating hardware, to the systems that we're trying to run. Typically, that separation, between this virtual asset versus the actual bare metal is usually defined by a hypervisor. The way containerization is different is that, in containerization, there is certainly a runtime environment. However, when we spin up those, containerized machines, the way that they are different is best summed up metaphorically. With a virtual machine, it's almost like we're slicing up a pizza, right? And you can make your slices as big or as small as you like, but there's only so much of the pizza to cut up. With containerization, it's almost like there's a bowl of soup and everybody has a spoon, and you can take as much from that bowl of soup as you like. There is no ceiling as far as the resources that are available. Um, really this distinction between virtualization and containerization is again down to this idea that again, are you dedicating hardware, or is hardware generally available for your containerized asset to run? When it comes to the Kubernetes environment itself, on the screen, I'm just going to kind of follow the arrows there on the screen, and we're going to go left to right. And you can see on the far left, I've annotated something called the control plane. Typically, the control plane is where you have a host that we typically call the master node. Um, And on the master node, we usually have several effectively just utilities that are running in memory. And just to kind of call out the one that most arrows are pointing to is this thing called the API server. The API server is really where a lot of the action is happening from in order to speak to any of the other components in the master node. Components that are not part of the master node have to speak through the API server. In order for the components within the master node to speak to each other, they have to speak through the API server. Again, kind of sliding a little bit there to the left, we can see there's etcd is annotated. And etcd, what that really brings to the table is effectively data storage, but it's done in like a key value pair. An example of a key value pair would be something like a key would be a name. And then a value that might be associated with that might be, as an example, my name, Peter Starfinger. And so etcd is really just a key value database that is storing all the different configuration items for Kubernetes. Right below etcd, there's the scheduler. And what's special about the scheduler is that it actually has a very special role where it communicates back to the API server where a workload can be placed. And it makes this determination based on utilization and different priorities that might be configured in the system. But this very distinct role of deciding where something runs is the job of the scheduler. Then there's something called the control manager. The control manager also has a very special role, and its role is to assure that any workloads that are deployed into a Kubernetes managed environment are actually meeting whatever their designation is from an availability point of view. In the control manager, I'm calling all these things a utility. There's lots of little sub control managers that make up the control manager that align to the different kinds of resources that you might create inside of a Kubernetes managed environment. Now we can also see kind of towards the bottom, there's that little greenish box, and what that's meant to represent is a console. And really, what we're showing there on the screen is some of the same things we covered when we're going over Docker forensics as an example, where there's kind of a primary utility that an administrator might use, and in this case, it's called kubectl. And typically, the way that you're issuing commands, it looks a lot like Docker commands. There's always a verb noun combo. Now, whenever we issue a command with kubectl, it has to speak to the API server, and then from the API server, that's really where all the other action is happening, which we'll get into when I talk through the actual orchestration piece. All right, we're going to slide to the right now. A little bit of a presentation fail here. Again, this is how this works. But in the center, we can see that there is a note where it says nodes, and then in parentheses, it says workers. So really, all the little boxes represent worker nodes, or AKA hosts, that might actually be running something called a pod. Now, we also call this the data plane. And so typically there's a separation between the control plane and the data plane, because the data plane is really where all the action is occurring as far as services we might create, that would be used, in conjunction with, containerization, type technology. We can see inside the worker nodes, there are some really important components, and definitely want to comment on them just a little bit. One of those components is the kubelet, and it has a very important role to talk to whatever the underlying container runtime is, in assuring that whatever containers need to be spun up as a part of, and I'm going to introduce a new term here, a pod. Whenever a pod is actually sent out into the data plane, again, that kubelet has to make sure that the right containers are created as part of that pod's existence. Now, when we talked about Docker forensic, a container was really kind of one of the most atomic units, if you will, from a Docker point of view. Well, from a Kubernetes point of view, the pod is the most atomic unit. And again, it's what encapsulates what we learn from a containerization point of view. We also have something called kube proxy, and kube proxy, where the kubelet is more oriented towards assuring that uh, those pods are coming up and being created. The kube proxy actually has responsibility for assuring the network connectivity, back to those pods. And so once a pod is actually brought to a state where it can provide a service, that communication is usually sent back to the API server, which then the kube proxy would see and then start to implement what's necessary in order for the networking side of these pods to function, or more importantly, the services that they're providing. Also on the screen, we see a reference to our good old container runtime environment, and again, more of the same there. But most importantly, that's bundled inside of the pod. And then, of course, we also have a reference to the image registry. Now, we're not going to cover off on that again, but the image registry still plays an important role. Again, Kubernetes, the role it's filling is, making sure that, when we do create services, that those services are up and available, and again, robust, based on their definition. But all those services, again, they're built on top of pods. Pods are built on top of containers. Containers are really built on top of the images that are stored inside the image registry. All right. So let's touch on container orchestration. Again, to the kind of far left, we're going to read left to right again. We can see our little console screen again, and we're going to go with that must be a developer working the keyboard. And right next to that, kind of that green console, where again we see the kubectl tool being referenced. The example we're trying to show here is a deployment being created. And just to kind of address, what's inside of a deployment, we're still using, a deployment is a type of resource, but we're still using manifests or infrastructures code, just like what we saw with Docker files. But the structure here is just a little bit different. You kind of have three different portions of the configuration if you look on the screen. And it's down to a section called metadata, then there's the specification, and then there's the status. And just kind of peeling the layers back there, the way that Kubernetes, when you're writing this infrastructures code or creating a manifest, we always have to say, what version of API we want to use within our file. And then we usually define what type of resource we're creating by using, again, this key value pair of kind. And so we can see that the kind is deployment. And then in the metadata, this is usually where, we kind of write out, right, we give the deployment, a name, and then we also use a important feature of Kubernetes, which is labeling. Now, labeling really allows us to tie things together, and it'll definitely come up a little bit later. And then underneath the specification itself, we actually see what's necessary for this deployment to function within the Kubernetes environment. And here, there's a statement that there needs to be 3 replicas. And what that really means for our purpose is that there's going to be minimum 3 pods that are up running, that are going to host this service. And then we see that there is a selector, and the selector here is saying, well, make sure you match the label for the application Nginx. And then we also see a reference to a template. And, when we talk about, the template, again, we still establish the metadata, because in the metadata, we can define labels, which we can use later to build other things around it. But then we also see the specification for the underlying container. And in this example, the containers are given the name Nginx. They're using the image Nginx, and again, you can see the full version there. And then finally, there is a service defined by the container port they are being exposed, which is going to be port 80 in this case. Now, rolling back up, so we can see from the green console screen a communication going out, and it's an HTTP post over port 8443, and that's going to the API server. And in that initial communication, this is kind of being read, top to bottom by the API server. And so, kind of that first piece that's picked up is, hey, this is a deployment that does cause a communication to go over. Now, earlier we mentioned the control manager. Again, in the control manager, that big bulky utility that's running in memory, all these little pieces, parts for all these resource types are inside that one binary. And so, communication goes to the deployment controller. The deployment controller interprets the bit of that manifest that's applicable to it, which again points back to a replica set that causes a communication to the replica set controller. Again, from a replica set controller perspective, there's 3 instances of pods that are going to be created. From a pod perspective, we have to know, where are those pods going to run? So a check is made back to the scheduler. The scheduler communicates back to the API server, which actual worker node can host this workload. And then finally, we have the call in from the kubelet. Kubelet sees that it's designated to run some pods. It pulls down the relevant information for that, communicates with the container runtime environment, again, creating whatever containers are necessary for the pod to exist. It communicates the statuses of those builds from the runtime engine back to the API server. Once those pods are ready, the kube proxy, which is another agent again running on that worker node, will see that the pods are ready, and then the actual IP information associated with those pods, and the kube proxy will take it the last mile, which is connecting what's called a cluster IP, which is a virtual set of IP addresses. It'll actually create the mapping between those virtual IP addresses back to, again, the exact endpoints, the containers that are running on the worker node. Now, the kubelet does have one other responsibility, and we're not going to get heavy into it this time, and you'll see later that I left it off, but the kubelet also, after an IP address is assigned, it does communicate back to something called core DNS, and effectively creating a DNS entry that would match, our labeling that we saw back in our manifest. And so, in this example, you would have an entry for that Nginx. All right, and then really, once everything is up and running, this isn't really represented here, but at any time, the API server can always reach out on behalf of the controller and check the kubelets to make sure that the health status of the running pods is still in a state of readiness. And then, of course, if not, the controller from there forward will always make sure that there's at least 3 instances of these pods running in a healthy condition. Now, getting into deployment options, a lot of great options here. And just to kind of touch on them, you could definitely, do an infrastructure as a service with one of the major cloud providers, and totally build Kubernetes yourself. There's a lot of deployment tools that support that, and of course, you could self-host as well. Some of those tools include things like Kube8M, and this allows you to really just bootstrap, the hosts that you need to, either run as a master node or a worker node. There's also some other options, which I didn't spend a lot of time with, but Kops and Kubespray, and really, Kube8M, I would just say is probably maybe better for a developer. I think it's good for experimentation. When it comes to Kops and Kubespray, that's something that's actually made by the community, so you can do a production ready version of Kubernetes. Also, from a SaaS point of view, you know what? A lot of cloud providers out there. I list three on the screen, but if you check out the Cloud Native Computing Foundation's landscape guide, they actually list hundreds, and it is a lot. I mean, just hundreds of potential providers that are certified to run Kubernetes. And then finally, there are educational deployment options. And definitely, I leveraged a lot of this myself. As mentioned, Kube is, in my opinion, really a really good fit for a developer. I think even friendlier for developers is Minikube or Kind. Really, the difference there is that when we talk about Minikube, Minikube, you kind of get like an all-in-one build of your master node and potentially worker node. In Minikube, you can point it at whether you're going to use a hypervisor to build your infrastructure, or even use a containerization service to build all your infrastructure. Kind is Kubernetes in Docker, and so you kind of come out of the gate, with your infrastructure inside of Docker, and so that is a little bit of the separation there between Minikube and Kind. Again, both super easy to use. Moving along, so from a Kubernetes security point of view, there's definitely some considerations. This isn't a security talk, but you know what? This is cyber defense oriented, so we should probably mention some of the security features. There's lots of different authentication plugins, and again, we all know about authentication in the sense that if we're running, an environment that's going to have workloads, as an example, that might be PCI based, or maybe the data there is very, sensitive. Again, we should probably, take the time to select the right authentication, plugin, based on the data that we're really trying to protect. And then same thing with next step, right? We can always program, we can always write with our infrastructure's code, something called a config map, where we can define different secrets. But the challenge herein is, are those protected? Now, within Kubernetes, there is an effort to have those secrets, in a protected state. But in my opinion, just hands down, I think the wisdom is really with if you're going to have secrets that you need to share among any of the infrastructure components, which we really covered off on earlier with the Kubernetes environment overview, or even within your pods, right? Try to leverage a modern secrets manager for that sort of business. And really what that gives back to us when we use a modern secrets manager, it's a lot easier to rotate the secrets that need to be used by these services as we're building them. And then also RBAC, again, assign roles as needed. When we talk about cluster roles are a little more oriented towards the underlying hosts themselves that we're calling nodes, versus can also have roles that are much more exclusive to whether we have a person who needs to just interact with Kubernetes to build a new service or a new workload, or maybe even you have CI/CD environment that you want to integrate. And so again, making sure that the CI/CD environment, right, if we're going to do continuous deployment, has just the permissions it needs to get its job done. And then just kind of breaking out from that, again, when it comes to node security, we can still do a lot of isolation, from a network point of view. An item not here at the top. We can do things like, network policies, and use, earlier I was pointing out this idea of a label, right? We can do like a label driven security, where we could say that, an app with this label should be able to speak to something with this other kind of particular label, and things like that. Also, security context, again, we can set that. We can also make sure that our pods are always set to run, not in a privileged mode on the worker node, right? We don't want to give them full administrative access of the underlying node. We can also make sure that when it comes from a file system perspective, that really the only accesses the container has is to whatever's defined as a part of it, but not necessarily any of the root directory, as an example, on the underlying host itself. Also, kind of outside of network policy, there's also pod security policies. And what's great about these is that there's different levels of security you can set, which also includes a mode where you can, and again, this is powerful in a dev environment, right? We can spin up a machine and then turn on, this pod security policy into a monitoring mode and actually see if it creates any impact to our application. And so, the pod security policies, can eliminate things like, pods running in a privileged mode, or, having like root file system access and other things we really just wouldn't want, in order to, again, minimize what our exposure is anytime we do have any of these pods up and running. And then also there's, companies out there that are offering things like service meshes, and that's where, now we're almost putting like a web application firewall, or a proxy container, if you will, inside each one of our pods, that would then restrict and control communications that's going directly into our pod. Again, using a rule based language to limit and control that flow. As far as what are the new opportunities for us as forensicators? Well, just want to point out, anything in blue I'm not covering here, so definitely an opportunity here for a second talk. Have to leave some things off. This one's pretty lengthy, but really on that master node, definitely etcd. Again, anything that's created in the Kubernetes environment, it's going to be stored inside etcd in a key value pair, and so that's powerful if we're able to again get our hands on that database. Also, the control manager, ended up finding a lot of forensic artifacts. But what's special between etcd versus control manager, the API server, and the scheduler is that most of the forensic artifacts that I found were memory resident only. There wasn't a lot of activity happening on disk. And then when it comes to core DNS, again, core DNS is really important. This is how we're able to find our services and pods out there. Core DNS, really allows us to not have to worry about, or especially our developers, right, have to worry about whatever random IP is assigned to a pod. Again, all that's handled as part of the orchestration process, which again would cause core DNS to be updated with wherever the new IP location is for a particular pod. Now, as far as the worker nodes themselves, again, the kubelet and kubeproxy, they're creating all kinds of artifacts in memory and disk. Definitely excited to show those to you. As far as the setup and all those administration utilities we called out earlier, in my opinion, if you're seeing setup utilities, there's just like we talked about, Docker forensics, right? We showed a lot of utilities that are used to create, natively through the runtime environment, the different resources that might get used. Same thing here. And so, though this talk isn't going to cover it, there's some commands that are going to be more sensitive than others. And again, if you have an endpoint that has these tools, you probably want to look for, the utilization of those tools to, again, delineate, right? Do we have an adversary that may have been abusing the use of those utilities being left lying around, or maybe potentially an actual insider. From a pod point of view, again, there's a lot of opportunity here. There's something called the network endpoint container that exists. So there's always, even if you create one container that's running the service that you meant to bring up live, there's always this network endpoint container that's running almost side by side isn't the right term, running in line with your container that's actually hosting the services that you meant to expose. And then finally, pod logs. And look, just to kind of shortcut to the answer here, or what it looks like. When we looked at, what logs are available naturally from a container that gets created, and the container runtime environments, it's effectively those same logs, and so that's definitely an advantage. Just kind of breaking it down a little bit more, again, from an API server perspective, definitely interested in, the API server log file, if it's available. And again, anything that tells us about, the Kubernetes configuration. And so I kind of did, what the prefix looks like if you're hunting for that. And then, again, I do call it out here, though we're not going to look at it. Core DNS, it has its core file. And core file is really, again, just a number of conditions that deals with, how DNS resolution is going to occur within your Kubernetes environment. And typically all things result in, if I don't resolve it, here's the, if I'm not the resolver for it, here's the external server that'll handle the query. Again, from a scheduler point of view, definitely interested in that scheduler log if it's available. And of course, whatever the scheduler configuration is, those configuration files, again, give us clues when we're trying to look for deviations. If we do have somebody who was able to do evil on our master node, control manager, again, looking some very similar things. And for etcd, like any database, right, we have our write ahead logs in a file, and we also have the actual database itself, which is a type of snapshot, and we'll be looking at that a little bit later. When it comes to the worker node, again, the kubelet, there's the kubelet log itself. There's also the kubelet configuration. There's a lot of great clues there. And then also, how is the actual, agent set to run on the worker node itself? Looking at those, configuration definitions, again, give us a lot of clues, whether we have something that's been introduced to potentially persist that somehow makes the environment more vulnerable or usable for an adversary, or the other side of that, if there may have been some other weakness that was abused, worker node side. Again, we can spot some of those deviations by knowing how it should be set up. From a pod point of view, again, all what we talked about, again, check out my Docker forensic talk, and the Docker forensic cheat sheet that's out there that I've created. All that container forensic stuff does matter. Now, there is a little bit more here, and a lot of those connected pieces when we talk about pods are in particular folders. But really, if I had to oversimplify it, all there's really just a bunch of symbolic links that are pointing back to what we've already learned exists, in a container runtime environment. And then finally, logging around the pods, definitely want to take a look at that. And when it comes to the proxy itself, we do have a number of configuration files that have to be created in order for the kube proxy to work. And again, the kube proxy log itself. Also, IP tables are a big part of this. In order for the network communications actually flow inside of Kubernetes environment, again, those IP tables have to be manipulated. And then from the container runtime environment, we also have a network database that's also tracking what containers have been assigned, what IP addresses. And so a lot of great network clues that are all related to, again, the kube proxy being able to do its job well. And again, setup tools, just calling out where it is you might look for the setup tools, and then maybe some files you're interested in. Again, I'm not going to cover off on that here. All right, so here's your map. And again, we're going to use the naval compass here to glide around to the different pieces, parts of the Kubernetes infrastructure. And again, starting, with the API server, right, put a lot of emphasis on that being important. And, really, if I'm letting my eyes do their job right now, you can see the direction that communications can flow. Now, again, small fail here. There should be an arrow pointing back to the kubelet from the API server, because not only does the API server have different APIs that can be interacted with, but the kubelet itself actually has a limited API as well that's used by the API server to report back to the controller statuses on pods. All right, so on the screen, and look, there's gonna be a lot of rinse and repeat here as far as the way that I approach this. The big thing is that I'm using the tool volatility, and I'm the volatility framework, and the modules that I kind of consistently use include PS tree. And the reason why this was important, the utility that I decided to use to build the environment was the Minikube. And so I used Minikube in conjunction with Docker in order to build the analysis environment for me to discover a lot of the forensic artifacts I'm sharing today. And so when you see the module being called Linux underscore PS tree, really I'm just kind of starting at the top. I'm looking for, the runtime environment, and then I'm looking for, what container is associated with it. And then also any of the processes that have spawned as a part of that container existing. I'm trying to look at, what the command line is, which is the PSAUX plugin being called. And finally, the PSENV, I'm just looking at what the environmental variables are called. Now, why is this important to us as forensicators? Now, all of this was pulled from a memory image, and when we capture the memory images, we can look and see the way the environment was set up to run. Now, what's really powerful about Kubernetes is that all these switches are very well publicly documented, and so you can use, when you're looking at the API server, you can use these definitions behind each one of these switches to understand the security of the environment, based on how the parameters are defined. And, the same thing from, we start thinking about environmental variables, again, we can see things like, what library path is it loading from. We can see what the actual, some network definitions, like what is the underlying, host name for the master node, things like that. Kind of the next slide, here I'm just using the netstat plugin from Volatility Framework. And, what I was after is, I was showing earlier in a slide, that communication from the console to port 8443. um, I would completely expect any connections that are happening to come into 8443. Now, as a forensicator, what you would want to be concerned with is, do we have a connection to 8443 that's coming from, as an example, a foreign IP, right? Um, I think I was doing some spot checking, and the shadow server project identified there were some hundreds of thousands of these API servers that were exposed to the internet. And so that's pretty scary. But for us, hopefully you're going to come into an ideal situation where, again, the administrators have reduced, the network footprint as far as where connections can come from. And again, you can, interrogate that to determine, again, do we have potentially a connection coming into the API server that we wouldn't expect? And then building kind of outside of that, we can see there's a lot of established connections to port 2379. And really what that is the API server speaking to etcd, which is what we want it to do. Um, as far as, what was to me very powerful with respect to the API server, I found, simply by going into the memory space that was, allocated and doing string searches, I was able to use things like, the prefix registry and then the resource type that I was concerned with, and get a full listing, of those resources and their configuration right in memory. Um, you could even go so far to break that down by a particular namespace. And a namespace is really a way that in Kubernetes or an orchestration environment, we can organize our workloads. And so by namespace, like let's say there's a particular workload we're concerned about, we can look at resources by just using the prefix that's on screen. The other thing I thought that was very powerful is that, in the public documentation for Kubernetes, there's all the API interfaces are predefined. Well, if you have an image of the server that was running the API server utility, you can actually use the API definitions to just do the queries in memory. And so really enjoyed that. And from my point of view, what this really opens up is that you can use the actual API, you know, defined surface to do Yara like searches to get the information that you're after, or just do these keyword searches as I have them listed on the screen. From a disk point of view, look, I'm not going to show a lot of this, but as I mentioned earlier, I was using Minikube, and then I pointed Minikube at a Docker runtime environment that I had installed on the box that I was doing my research from. And really, what's on screen here is that you can see what folders are being mounted to that container. And when I went through those folders that were being mounted, besides the configuration files being present, there was not a lot of activity on disk. And again, I ended up using a lot of what I spoke about from the Docker forensic standpoint, where I was actually doing differential analysis from the original image that created this container that was running, with the API server. As far as, and look, you'll see this for each one of the utilities. I'm just grabbing the actual container logs and just showing they exist. Here you can see some of the interactions that were coming into the API server. So not going to go through those logs, but just remember, if again, there are logs that you can grab, especially if you've containerized the actual utilities that make up your control plane. Moving along, again, just following that naval compass, we're going to take a look at etcd. Again, just a reminder that's where we're storing effectively the entire configuration for the whole orchestration environment in key value pairs. And so, with that being said, again, we have our standard run-of-the-mill plugins that I run from Volatility, and this is just me discovering, again, what configuration has been created. Things that I really keyed in on was the location, for instance, of the actual database itself. That did give me an on-disk target, just in case the database was not memory resident. And also I was able to kind of see some of the configurations as far as, based on port. As an example, 2379, I would only expect, the API server to speak to it, but there's also port 2380. Well, what's the purpose of 2380? It's so peers can, if there's more than one server that's running etcd, over 2380 is how they are communicating, to each other. All these little details, which again, if you pair the switches that we find in memory with the documentation, you can see how the environment should function, based on this configuration. Kind of moving along, when I took a look at, what files were being accessed, again, what jumped out was the actual location of the Snap database. Now, conveniently in the command line, we did see where we could find that because it was in one of the switches. But what's really important here is that we spot both the database as well as the write ahead logs. And again, from a network point of view, a lot of listeners here, again, just going back to 2379 because it's easy. 2379 is where we'd expect those kind of client to server communications to be occurring from the API server. Again, 2380, I would expect communications there if there were other etcd databases. And then 2381 is really health related. From my view, if I saw a communication that was anything but my API server or another documented etcd instance that's part of the deployment, to me, that's a big clue as an examiner that I may have some, nefarious activity going on, the machine that I'm examining. As far as memory versus disk, so so much power here, and it's kind of the power you would expect, right? etcd where all the configurations are being stored. From a memory point of view, one of the things that I did on screen there was I just searched for all the containers that are in memory by looking at where the Docker runtime was executing, and then what the unique identifier was for the container in memory. And when I did a spot check against, in this example, it's the write ahead logs, I was able to see not only the location, again, using the key phrase Docker dash pullable, not only the location where the image was pulled from to create the container, but I could also see every container that was being tracked by etcd. What's the power here? When we look at etcd, if you have a managed pod, and inside that pod, there's going to be containers associated with it. What I would never expect to see in a production environment is where we have containers running that are not being tracked by etcd. To me, I would call that low hanging fruit, right? Or if I looked at the registry where the images came from, and that registry was not one of the authorized, like it's a really bizarro, maybe FQDN or maybe a foreign IP address that isn't part of the environment as you understood it. To me, those would also be targets for potential rogue infrastructure in an environment. Again, just looking at the difference between memory and disk. In memory, I just kind of did a quick grab there to look at what else is disclosed to us, and something that is disclosed to us, and this is where it gets a little bit scary. If you have an adversary that has managed to get onto your master node, we can see the location for the key. Now, what's on the screen is just me showing, even for etcd, that configuration that etcd has is also stored in the database. And so for all the utilities that make up the master node, you will find that stored inside the database, was my observation here. And then when it comes to pods themselves, again, we're using that Docker pullable as a key word here. If we just look 3 lines before that, we can actually see the name of the container itself, and then we can also see the IP of the worker node as well as the IP address of the pod. And so if we're looking back from a data perspective and considering, did we collect the right systems? Again, knowing, the IPs of the worker nodes that you might have collected that were of concern, we can now start to map, if there's a pod that gives us concern, to the right worker node. As far as resources are concerned, whether we're talking about the Snap database or the write-ahead logs, to me, I saw a lot of the same action that I did from the API server, which makes sense. You could use that, again, that prefix, if you will, of registry, and then really follow registry with whatever resource type you're interested in. And again, I'm just highlighting one more time Docker pullable here. The other thing that's just kind of interesting, as I mentioned earlier, in the command line for the utility etcd that's running in memory, the configuration or that secret is actually stored in the database. And this just goes back to some of my advisement earlier. Here you can see I'm just doing a check for a token that was mentioned in the command line, and I get this base 64 decoded encoded value, and really I could just decode that, right? That's not any kind of security. So again, if you're working a situation where you got a memory capture, or maybe there's an EDR solution you have, and you're looking at network connections coming in the environment, and you see those foreign connections. Again, any secrets that are being stored in that database that aren't in your secrets manager are now potentially at risk. As far as database recovery, so a lot of what I was showing was using, volatility framework, and really just getting on disk and using tools like find and grep and things like that, and that's powerful, But something else that's powerful is that, if we have a disk image, of a machine that was running etcd, we can actually um, restore the database where it's live, so we can use native utilities to query against the database. Now, on the screen, I decided to have a little bit of fun. Obviously, my first go couldn't possibly be successful, and so what happened to me when I attempted to do a database restore that I could query against, I actually ended up having a fail where the version of tool that I was using, the etcd cuddle, was actually a higher version than the running version from the live environment. And that's really what you see in step two, is it throwing me a very verbose error message, letting me know what I have to do if I want to use that tool. And well, when I did get it right, all of a sudden, the data on the screen changed, and I had a much greater wealth of JSON coming on the screen, again, giving me a pretty good visual cue that I'd done it right. Now I had this etcd instance up and running with the database I was interested in. And here I'm just using, again, that native etcd cuddle tool to now query against the database. And look, it's all verb nouns. Here I'm running a git command. I'm saying, starting from the top of the database, um, you know, get the prefixes, show me the prefix, right? And then show me the keys. And then I pipe that through grep, and I flag that I want to see all pods that are running in the default namespace. I chose that because I would never expect in a production environment for someone to use the default namespace to run anything that matters. And so to me, that seemed like a great place to go look. And again, when I did that search, I could then use etcd, right, to query against, the pods that gave me concern. And so on the screen, the way that syntax looked was just I ran, the etcd cuddle git command again. I specified the exact key that I wanted to see the data for, and I piped it through more. And on the screen are all the key value pairs. Now, what's interesting about this, at least to me as an examiner, is that everything in memory and everything on disk is ASCII, so it's really easy to kind of grep through. You could probably just run strings against it and kind of get down to the business. But here, because we're using the native tool, we can actually see the right data, if you will, that was meant to go with the resource that we're interested in querying against. And to me, that was really the value of using, the native etcd tools to do analysis against the database. All right, so just following that naval compass, we're going to take a look at the scheduler. Again, just a reminder, scheduler is where all the decision is made around what worker node should actually run any pods that are being defined by a manifest like we looked at earlier. Um, from a scheduler point of view, look, again, super interested in what the command line is, for the runtime environment. What it tells us, and this one's a lot simpler, obviously, than etcd or the API server itself. But what we can see here is where is that service binding at? Where are the configuration files? Again, those are going to be really important to us as analysts, because again, we need to understand, what's normal in the config in order to understand maybe what's abnormal. Again, also pulling, what connections were going on here. So we did have connections going back to the API server from the scheduler. Again, if we just think back to that diagram we looked at together, that makes sense, right? If we're following the arrows. Now, what I would not expect is a communication coming into 10259. My understanding is that's actually just meant for the system itself to have communications, locally. That's not meant for, as an example, for, some really any component to be interacting with it. So if I did see any communications here, or if the listener wasn't local host, I would be very curious as an analyst to follow up, what that network connection was all about, and also maybe interrogate a little bit to see what it was doing. From a config standpoint, again, here we see right in the configuration file, references to our actual secrets. And so this is a pretty big deal to us as an examiner. If we're on this machine, we had concerns that an adversary had gotten a foothold. I would say that these secrets are now at risk and probably need to be rotated as part of your remediation efforts after you achieve containment. Um, as far as finding resources, I found in the scheduler, not as great as etcd or the API server, but there was definitely a lot because, again, the scheduler's job is to designate where the pods will run. And so I was able to do a different query where if I started off with the namespace that I was concerned about, I could then specify a particular resource type, and I was still able to, identify, in this case, pods. Again, just showing because this scheduler was running as a container, so we had all those wonderful logs that are naturally part of that. When it comes to, so look, that was it. From a scheduler standpoint, just kind of button that up. Look, when I took a closer look at the config itself, there was not any portion of disk really being mapped besides a pointer to a folder on the host that contained the config. When I did it, that differential analysis between the image that created the scheduler versus, what was actually live on the machine. Again, there were no changes to disk, and the same is going to turn out to be true for our controller manager. Now, the controller manager, just to take you back, its responsibility is, again, to then act on, again, whatever the scheduler is designated as the worker nodes that will run the workload that's being created. But again, another very important responsibility it has to talk to the API server to then check on, effectively any services or deployments that are being created to make sure, again, they're all running in a healthy state. From a controller point of view, a lot of great stuff inside the command line for the controller. You have things like, as an example, the virtual IPs that should be used within the cluster in order to facilitate, routing within the Kubernetes environment between all the pods. Um, and so, kind of in addition to that, we also can see, what virtual IPs are allocated. As an example, if we start establishing services and how it is, we would create, again, connectivity to those services. We can also see things like secrets that are being used by the controller in order for it to talk back to the API server, right? Where are those located at? And again, a lot of great stuff in the environmental variables. Again, what we're after here is what is normal, how is the environment set up to run, and what is that looking like at runtime, and is there some kind of deviation? From a network point of view, we have a little bit of the same. Would not expect any communications to be able to come into that listener that we see on the screen, 10257. Again, that's just kind of a standard port. I would have expected communications to go back to the API server. And so again, here, all is normal. If you see more, it's not normal. Look harder. Here, I just, again, another spot check, just kind of showing, what was being mounted here. And again, what's really on screen, just kind of cut to the chase, is the only thing being mounted is the actual configuration files. Those are being exposed back to this container that's hosting the controller utility. On disk, just wanted to show, just like our scheduler, if some adversary was on the machine where the controller was running, again, this stuff is just kind of sitting there ready for them to grab. So, um, these secrets would definitely need to be rotated as well. And again, more of those lovely container logs. Okay, moving on here. With respect to in-memory things that we can check, just like the scheduler, just like the API server. We are able to do checks against resources based on their namespaces, and so again, to me, the advantage here is that we're always in the business of looking for what appears to be uh, managed and normal, and again, trying to find where are there deviations. Just kind of following again our lovely naval compass, we're going to take a look at the kube proxy. Now, just kind of a callback, again, kube proxy's responsibility is once the pods are actually up and running, it is looking for that kind of a status. And then the kube proxy actually creates the connectivity between the IP addresses that are being assigned by the underlying container runtime environment. And they're connecting those to the actual virtual IPs that are meant to allow this intercommunication between all pods that are part of the worker nodes. When it comes to kube proxy, again on screen we can see that lots of great stuff as far as infrastructure being defined, exactly where different kinds of connectivity should be at. Again, this is valuable to us in the sense that not only can we check each one of these switches to understand what normal is for a particular worker node, but we can also look at maybe where we have unexpected communications to those same services. From a listener point of view, again, we have that connection going back to the API server, and that totally makes sense. Really, that's again, the kube proxy does not function independently. It's completely looking to the API server for queues. And then we also have the service ports for just health listener. So if there's um, uh, for instance, I think there's another tool called Prometheus that's integrated with the kube proxy, and so you could use that to do health checks as well as get metrics about the actual worker node itself. And so I would expect maybe some kind of connectivity to be coming from either the master node itself or maybe authorized network monitoring devices. Now, you also have, whenever we think about something called a node port or cluster IP, and just kind of talk through that. So, cluster IP is really just a reference to that virtual IP address I was talking about. The way that all these pods are able to communicate to each other is, through this thing called cluster IP, which is a virtual IP address. Now, Node port is a little bit different. Node port is where we're actually now taking a pod and we're going to expose, a port from that pod via the host's network card or the worker node's network card. And so that's a much bigger step. A little bit of a jump there. So again, what we're interested in here from a config perspective, we definitely want to go look and see where all the configs are. We're always concerned with absolutely what's normal for the environment, but also what's potentially at risk if we do see an adversary on a machine, right? Because it is possible at this point you really don't know the full extent of the compromise. Um, and so by finding this config file, we can also start to spot what potential secrets are at risk and what the context is of those secrets. Here we have kube proxy that's again serving the default namespace. The other thing that's kind of interesting is we can see where the token file is, and so if we ever have any indications in memory that maybe that was accessed from anything but kube proxy, that would probably be of concern to us as analysts. And here's just the other screenshots of the actual logs. I was running those through JQ. In this example, I'm just using the Docker forensic kit. Again, that was from my last presentation. And just using Docker Forensic Kit, I'm just saying, hey, just show me the logs. And this is kind of the default view you get there if you're not using JQ. Just kind of jumping on, so what is in memory? So, pull up the man page, right, for IP tables. I feel like there's a ton of clues there as far as how IP tables might be used. And at the end of the day, kube proxy, at least for the environments that I set up, it was just using IP tables to create all that connectivity. And so here I'm actually just looking for a destination NAT, and we can actually see, this is pretty cool. So we can actually see where a NAT is being defined to a particular IP address, but we also see, the host name for service. And so pretty exciting stuff. But the bottom line here is that, if you carve for IP tables, you could probably find out what communications were authorized on that particular worker node. And just here, yeah, a few different things on the screen. Look, I'm going to start from bottom of the screen, just kind of work up. First off, just kind of looking at Etsy hosts for this particular device. Inside Etsy host, we can kind of see that there are some hard coded host values in there. That's always worth kind of checking. If we had somebody who may have been playing some hijinks, with our environment, I suspect that is a place for potentially, malicious modification. Something else that we're interested in is definitely, how um, uh, the network overlay, if you will, is being set up. And so, it's through this idea that there's the Docker runtime environment, but then there is a need to create connectivity from the Docker runtime environment back into that overlay network, that virtual network that exists, so all these pods can communicate with one another. And so, here I'm just using the volatility plugin, ifconfig, just to kind of see, what's defined, by Docker, what bridges are defined, what virtual network cards exist on the device, things like that. And then within, and this is specific to Docker environments, you have something called local-kv, which is a database that's actually tracking, all these IP assignments. Now, those IP assignments are actually communicated. Here we're looking at kube proxy, but those IP assignments for the endpoint are actually communicated back up by the kubelet, um, in order for, again, kube proxy to then make its decisioning on how to build those IP tables to create that connectivity. Okay, moving along. So going to take a look at the kubelet. From a kubelet point of view, look, here's the game day highlight. So we can see the actual bootstrap config file that was used to establish that a particular host is now a worker node. And so definitely, want to take a look at that if we're forensicating. And then we can also see, again, what its runtime config is as well, which includes what the underlying runtime containerization engine is. And again, that might affect how we do forensics. Again, my last talk only addressed Docker. Again, it is possible that maybe Rocket is used as an example, or some other containerization technology. We can also see, what the host name is, as well as, what interval, we should expect communications, and also, what the actual, worker node IP is. That's all right there in the command line. From a communication perspective, so there are several listeners here, and the big deal here is that we have the communication going back to 8443. We can see that as an established connection there in the netstat table. We can also see a listener on 10.250. Now, that is a limited API server, and I would only expect the actual API server from the master node to be communicating with that port. If you see foreign connections, I would be very suspicious of those. 10248, again, this is just a health port for the kubelet. And I think this is all to really just Prometheus at the end of the day, running side by side with that kubelet. As far as how accesses are done, so again in memory we can kind of see the little access tokens associated with each of the running pods, and again they're being mapped to temp FS, which means it's really just kind of memory resident only, um, but those secrets are in memory. Some other things that are kind of interesting, when we look at the actual runtime variables that were set for the kubelet, again, we can see, or is there some other kind of network plugin that's in use? Here we can see that CNI is being called out. We can also see, earlier when I was talking about opportunities as far as pod forensics, there's something called a network endpoint. So we can see the actual image that every one of those infrastructure pods is going to be built from. And so, to me as an examiner, just from a completeness standpoint, right, not only, would I be concerned about, any containers that were, created by our developers inside one of these pods, but I would also be very interested, was there any, unusual manipulation, maybe, from the actual image file to the running container that makes up this network endpoint. And then finally, the actual service definition itself. There's a lot of great stuff here. Bottom line, we can spot all of our configs for the running service, and so I would just be concerned as an analyst. Is there anything that's been added that maybe gives me concern? All right, moving along. Now we're going to take a look at, now it's pointing at the container. Again, a little presentation fail here. I should have a wrapper around this that says pods, and then inside that wrapper it says pods. I should be indicating that could be any number of pods, and inside the pods could be any number of containers. Okay. Again, pods are going to be our most atomic unit as far as resources are concerned. When we talk in terms of Kubernetes, again, very comparable to when we talked about Docker runtime environment, where again the actual container is the most atomic unit. What's interesting here is that I'm pulling up on the screen a particular container where I'm just declaring arbitrarily that, hey, it's problematic. Now what's interesting is, and I don't think I mentioned this in my last talk around Docker forensic, is that that container ID is immutable. It is uniquely assigned at that moment in time to the running container. So once we spot the container ID, um, again, if there's any concern we have around that particular container because of maybe it was a certain network connection coming into it, maybe there was an unusual binary, or maybe there was a syscall that the EDR alerted you to that was very suspicious. The point though is when we go back into memory and we start doing queries, in this example against the kubelet itself, we can actually connect uh, what Docker containers are associated, I'm sorry, what pod is associated with the container that's giving us concern. Once we've made that connection between the container and the pod itself, we can then do another check and find all the containers inside of that pod, which then kind of allows us to establish, if you will, a little bit of a blast radius, if there was something suspicious going on from, any one particular pod, I'm sorry, container. Um, the other thing that's kind of interesting is that we can also find all the containers inside the pod by using that identifier, um, and then with those memory IOCs in hand, now we can go back to disk and actually find all the containers that are associated with the pod on disk, which then allows us to transition to using our Docker forensic skills and our Docker cheat sheet, and now doing that level of analysis to understand is there some new malicious binary? Was there maybe execution of extra tools besides again maybe the application code that should have been running in that container, things like that. And even if we don't have the memory IOCs, if we do have a copy of disk, the bottom line is that the location of these pods is standardized so the kubelet can function. And again, we get that standard location from the command line, and that standard location where the pods are at, they're really just symbolic links back to the actual container locations. So really powerful stuff here if we're trying to, again, stitch together. Um, we have an alert on something that gave us concern, and we do have a clue, which again is that immutable identifier, which is the container ID. And again, I would liken that to if we're doing traditional forensics, having a MAC address or a host name. All right, so we're going to talk a little bit about incident response. Again, we can see, we still have our nice little naval penguin and our naval compass showing us where it is we're going. But we also have the hacker penguin, and we're battling over the master nodes and worker nodes in this example. So, in light of that, let's talk about kind of what's publicly recognized. When I say publicly recognized, I used OWASP. I felt like that would be a good resource for this. Um, and so, when it comes to worker nodes, some risk events that could happen is you could have something like, as an example, all of a sudden a shell running inside of a container. What I would expect as an example in any production environment, and more likely dev, right? Most developers, I personally don't believe are gonna make it necessary. Most administrators aren't going to be pulling shells up to containers running inside of any of their pods. So if all of a sudden we have a shell, to me that's almost like there's user interaction going on inside of the container. I mean that's a pretty big red flag. Again, things like the proc folder being mounted, that's a little bit unusual. If your EDR warned you of this going on, that's probably it's time to spring into action because somebody is really about to elevate their access, or maybe a sensitive file being accessed, like Etsy shadow, or maybe a location server side that secrets are being stored at. And then of course outbound network connections. Really when it comes to Kubernetes, most of the Kubernetes environment, those communications are going to be service oriented, and so the expectation is that there would be a client to a server communication inside of that Kubernetes environment, not a bunch of call outs going on. So if you have a lot of interactions going outbound from your Kubernetes environment, that's probably a pretty good clue that a container may have gotten popped inside one of your pods. As far as the master node, definitely just want to interrogate, what process activity is going on. Again, it would probably be more likely that there's going to be a standardized host that's going to run those different utilities that make up the master node. And again, we've called out, what those utilities are. And so if we, had unusual processes all of a sudden spinning up, right, that's probably a good moment for us to go check out, which should be a relatively unchanging environment on the master node, why it is we have new processes all of a sudden. Also, network communications among, the containerized services, I, from a application perspective, I imagine again, your developers are probably going to create things where there's a, an interdependency between, some of those pods, and there's probably going to be some pods that are actually, exposed to the world through, again, either a node IP address, or maybe you have a cloud service provider where there's a load balancer configuration. There are things that would absolutely be normal with everything that I said there. But if you all of a sudden have, like, for instance, a container that starts, I don't know, connecting to all other containers, right? All of a sudden scan activity, it's probably worth digging into that. And also unwanted API calls. The API calls are pretty well structured. For the API server, again, that is very well done. By the folks maintaining the Kubernetes documentation. Again, if you all of a sudden get what looks like a web pen test going on, it's probably time to kind of dig in a little bit more into those event logs, and and just make sure you don't have some adversary trying to conduct an attack. Um, to me, as mentioned, that master node, definitely shouldn't be exposed to the public internet. And so, I feel like this last bullet point is a pretty good one in the sense that, if there is an anomaly, it's more than likely a security issue. As far as incident response, when it comes to the master nodes themselves, there's some real particular steps we want to go through. And to me, what's really important in order to recreate anything that I've shown here, what we're trying to establish, what is normal as far as, memory activity, understanding the way that an environment was set up, understanding again, with a lot of those components, there isn't really much disk activity. You really got to get a copy of memory, and disk to do the kind of analysis that I was showing earlier. Definitely go out there, get audit logs for those system components if those are being stored somewhere else. And then as far as the memory capture is concerned, again out of the gate, when we're talking about that master node, we definitely want to triage and just make sure there isn't malware. Again, some good clues would be processes that we hadn't seen before, or maybe existing processes having call outs or interactions that were not previously present. Other things that we could look at are things like, and this is just kind of run of the mill memory forensic stuff, but we can check things like, what runtime libraries, do we have active, what kind of file handles do we have? Again, we saw that there was a pretty tight coupling between each one of the utilities that's necessary for the master node to function. And so if you have a lot of crazy file handles all over disk, there might be something more going on in that master node. And, environmental variables, open files, and again, checking those configurations, right? We just want to make sure there isn't, anything unusual. An example was when we were talking through, again, etcd analysis. What registries were the containers being built from, right? Is there a rogue registry there? Is there potentially um, outside of that, maybe an image type being used that is not normally production, or maybe a namespace that you don't recognize. As far as the host itself, again, still want to do that, triage for malware, leverage, things like Yara scan, things like that, so we can get some quick answers. Is there anything unusual on the disk? And again, we do want to check for malicious, modification of startup, of the resident system itself. We want to just verify the, standing configurations, and again, run timeline tools. If we're here because of a particular bad process or an unusual network communication, there's probably a timeline associated with that. That's probably a good place to start if we're going to check disk. And then finally, audit logs themselves. Always want to check our audit logs, for Kubernetes. Again, if you're using a cloud provider, that's probably readily available, and just again start to separate. Do we have, potentially, some malicious insider? Again, malicious insider could just be an account that's compromised, or do we have a compromise that happened some other way, but again, it was of your master node. As far as the data plane, just again shifting the focus here to the worker nodes, definitely, some of the same, and then there are some differences. The kind of the first thing is, if there's a particular service that we're seeing some unusual behavior around, we really need to get out there and understand, what nodes were assigned, to run, containers for that particular service. Once we know, what nodes are associated with it. Now, this next kind of step, we can do network isolation using those network policies I was describing earlier. And we could also, if we just have concern about the host itself, we could taint it using condone. Now, the issue with network isolation and tainting. Um, Now, tainting, you're really, all you're doing at that point is just, from a Kubernetes point of view, you're pretty much telling the scheduler to no longer use that particular worker node. And so a lot of that would more than likely, being invisible to your adversary. Now we're not in the home stretch yet by any means, because the issue is that something is compromised on that node, and you still don't know the initial point of entry. Now, a more aggressive move would be, again, using network policy to isolate. If you isolate or take any actions against, maybe you're down to a particular container that you're able to spot through your EDR, the minute you do that, you have shown your hand to the adversary. So there's kind of that risk. And then another parallel risk when we think in terms of production, if these are mission critical containers, you really need to, closely coordinate, with your production teams on how the response is going to go down. The big deal here is, step two is a step if you're really confident about the situation and the alerting that has led you to that situation. Now, absolutely get copies of memory and disk. We've talked a ton previously about container forensics, and then even here, we went a step further and we showed you how to connect actual pods back to the containers that they're made up of, and we showed you how to do that through memory, as well as disk, and of course showed some methods from a master node perspective to help you out with that. As far as examining that memory capture, we always want to look for, again, a rogue process that's out there, but we also want to understand, do we have any containers that are rogue? Kind of a rule of thumb that I gave earlier is, if it's not being tracked by etcd, it's probably worth looking at. If there's a registry in use that's a new to the team, probably worth looking at. Or if you have a container running with no image on disk, again, that's another clue of what it is you probably need to be focused on from a container analysis point of view. And again, when it comes to the container itself, we definitely want to check all the runtime libraries and handles and network connections. And really, what we're after is we're trying to understand what it is that has already happened from that container. We're also trying to understand what's at risk based on potential accesses that container may have back into the environment, and then also any data that container may have access to. And then finally, just understanding, what is going to be memory resident only versus, what actually made it to disk. As far as the disk image of the host itself, again, we always want to, go through that mapping exercise that I described earlier. It is possible that, containers have run already exited memory. And so a lot of my observation has been that the cleanup is pretty long running. So it's possible that there's still a lot of garbage collection that still needs to happen. And so you might actually find maybe some original compromised containers that may have exited memory. Um, Also, again, whether it's memory or disk, we definitely want to check and see what else was at risk on the system. And, do we have any indications that, maybe an entire rogue pod, which is a pretty bad scenario, or just a rogue container, right? Was there anything done by that particular container that would create risk for the environment? And then also check that image source. Again, the power of doing container forensics just out of the gate is that we can do this differential analysis and understand what new data and what new binaries were introduced to any particular running container when we have access to an original image. um, and the rest of this is just more of what we know from a Docker forensic point of view. But again, just timelining and reviewing the config, and really just trying to wrap our heads around what opportunities were just afforded to our adversary, and do we potentially have a bigger risk here outside of whatever it is that drew us to the particular worker node that we're reviewing at this time. Look, the big takeaway here is if you can find what the initial point of access was by the adversary, this will allow you to get quicker, not only through containment, but more importantly through remediation. So again, you can stop whatever the compromise was from happening again in your production environment. Look, just a quick shout out here. Marco's book really helped me a ton with everything you just saw today. I just can't say how big of a deal this book was to my learning. Also, Tech World with Nana. I got so much mileage out of her GitHub and her YouTube videos that really helped me get through the portion of building resources that I could react to, but and study, and of course share with you. And then finally, the Kubernetes documentation itself. Think of a topic, put it in that search box, and you will be pleasantly surprised how well documented Kubernetes is. Tools that I used for everything that you saw today includes the Sleuth Kit. I also used, again, volatility. You heard me reference it dozens of times. And then also the Docker Forensic Toolkit. That still feels like my go-to tool whenever I'm analyzing containers. And so I highly recommend you check it out. I think it's far superior to Docker Explorer. And then again, just kind of a big shout out, Shaw. Thank you again. He's over Microsoft. He's a threat hunter there. He actually works with Azure and the cloud infrastructure there for their offerings. Also, Eldon Myers, another member of our community, spent a lot of time checking all these exhibits I was creating. Also, Chris Lamberson, again, thank you. And Casey, you two have just been supportive through so much of my research and just helping me get it into a presentable state while I'm working through the data that's available. So I guess with that being said, this is kind of the end of the formal part of the presentation. I don't know if we want to stop the recording so we can do questions.